Hello everyone. I hope you all are safe in this COVID-19 crisis. Today we are going to see the remaining part of this chapter, which includes moment of inertia, derivation for rotational kinetic energy, application of moment of inertia, radius of gyration, and expression of angular momentum in terms of moment of inertia. Before going to start moment of inertia, we have to know the concept of inertia. We have already studied inertia in 11th class, which is inertia is word we use when we talk about matter and moment. Basically, our idea of inertia goes back to Sir Isaac Newton's first two laws of physics. An object at rest tends to stay at rest, and an object in motion stay in motion. Inertia is a quality in matter that lets it stay still if it is still, or keeps it moving if it is moving. If you want to overcome inertia, you have to apply a force. Force will make something that is still start to move, like flicking a wad of paper with a pencil will make it move. Also, force due to resistance will slow or stop something that is already moving. The wad of paper will be slowed by resistance made by rubbing up against the air it is passing through. There are three types of inertia. Number 1, inertia of rest. When the resistance is offered by the body to continue in the state of rest unless an external force acts on it. Number 2, inertia of direction. When the resistance is offered by the body to continue the motion in the same direction unless an external force acts on it. Another good example for this is a cricket. When a bowler bowls, the ball goes in a direction towards the keeper. But when the batsman hits that ball hard with his bat, then ball will change its direction. Number 3, inertia of motion. When the resistance is offered by the body to continue to be in the uniform motion unless an external force acts on it. In shortly, an object will continue to be in the state of rest or in a state of motion unless an external force acts on it. Now, in terms of moment of inertia, it is defined as a body's tendency to resist angular acceleration. The moment of inertia of body about the particular axis of rotation depends on the following factor. Number 1, the density of the material. Number 2, shape and size of the body. Number 3, axis of rotation. In a mass moment of inertia, we have to see some important thing. It is a measure of distribution of mass of an object relative to given axis and denoted by I, capital I. For a single particle, its formula is I0 is equal to mr square, where O is the axis of rotation and r is the distance from axis. Its unit is kg per meter square and dimensions are m1, l2, t0. In translational or linear motion, the force depends on mass. But in rotational motion, we have to consider mass as well as its distance from axis. We are studying mass moment of inertia, which is given by I0 is equal to mr square, where O is the axis of rotation and r is the distance from axis. These are few properties of Mi in which Mi considers the advance distribution. Mi considers the distance-wise distribution of mass around the axis of rotation. Like other analogies, Mi in rotational motion is analogous to mass in linear motion. Means, for example, Indian currency is rupee and American currency is dollar. In similar way to that, in linear motion, what we can call mass, we can call it moment of inertia in rotational motion. Both of these express a body's tendency to resist motion in angular or linear. Mi depends upon following factor. Those are mass, shape and size of body, distribution of mass in body about an axis of rotation, and third is position of orientation of axis of rotation. This question will be asked for 2 marks with diagram and formula. Here are some physical significance of Mi. To produce linear motion, an unbalanced force is applied. Mass of body opposes this motion, thus mass provides inertia given by F is equal to ma. Similarly, in rotational motion, to produce rotational motion in a body, an unbalanced torque is applied. In this case, inertia of the body is called rotational inertia or moment of inertia. As I told you, analogy. Here is the analogy for the force. In linear motion, to change the position of an object, we need some kind of unbalanced force, and we define it as F is equal to ma. But in a rotational motion, to change the position of an object, here also need a force, but here we called it as torque. It is another analogy. The relation between moment of inertia I, torque tau and angular acceleration alpha is given by tau is equal to I alpha. We conclude that moment of inertia plays same role in rotational motion as the mass of the body does in linear motion. Here are some analogies between linear and rotational motion. In linear motion, we represent displacement by small x or s, while in rotation, the displacement is calculated in the form of angle. Therefore, we denote it as a theta. In linear motion, we represent velocity by small v, and in a rotational motion, we represent velocity, which is angular velocity, by omega. In linear motion, we represent acceleration by small a, while in rotational motion, the angular acceleration is denoted by alpha. Here is in linear motion, we called it as force to change the position of an object, and in rotational motion, we called it as torque. Similar way for mass and kinetic energy. Now, from figure, consider a body has a random shape and having n number of particles and distance r1, r2, rn. From axis of rotation, let omega be the angular velocity. It is rigid body, means the distance between any two points inside body is constant, that will not be changed, and axis of rotation is perpendicular to paper. When the body rotates around its axis, each of these particles perform uniform circular motion around this axis with same angular speed omega. But as r, which is distance from axis, is different for each particle, they will have different translational velocity, and their formula is v is equal to r omega. Let these velocities be v1, v2, vn is equal to rn omega by the formula. Let us consider translational kinetic energy for first particle. Kinetic energy is equal to m1 v1 square upon 2, but v1 is equal to r1 omega. Therefore, kinetic energy for first particle is equal to m1 r1 square omega square upon 2. Similarly, for all other particles, we shall have translational kinetic energy 2v. Kinetic energy for particle number 2 is equal to m2 r2 square omega square upon 2. For particle number 3, it will be m3 r3 square omega square upon 2, and so on. For the nth number of particle, kinetic energy will be mn rn square omega square upon 2. We know rotational kinetic energy is equal to sum of rotational kinetic energy of all particles represented in body. Therefore, rotational kinetic energy is equal to m1 r1 square omega square upon 2 plus m2 r2 square omega square upon 2 plus plus mn rn square omega square upon 2. Here we get half and omega square as a constant, as a common part, and remaining part is m1 plus m2 r2 square plus plus mn rn square. But we know that m into r square is equal to I, which is moment of inertia. Therefore, rotational kinetic energy is equal to half I1 plus I2 plus plus In upon into omega square. Therefore, rotational kinetic energy is equal to half I omega square, and for the comparison of linear motion and translational motion, here we are having formula for the linear motion or translational motion is 1/2 mv square, while for the rotational motion it is 1/2 I omega square. Here m is replaced by I and v is replaced by omega. This I is equal to summation of m1 r1 square or mi ri square. I is equal to 1 2 3 4 5 6 7 8 9 n of an object depends on their masses and distribution of masses about the axis of rotation, which is distance from the axis of rotation. If we have a different axis, this will again depend upon mass distribution around the axis, and if the object is not symmetric, it will be different for each axis. In reality, we usually have homogeneous rigid object. So instead of summation, we use integration, that is I is equal to integration of r square dm. Further, we will study mi for different objects like mi of ring, disc, sphere, rod, etc. Here we are going to study application of moment of inertia in detail, that is mi of ring and mi of disc. Here we know this formula I is equal to integration of r square dm. In a theoretical manner, if we do not know the mass of this object, then we are unable to calculate or solve this integral. But we can find it as experimentally. Let us consider the application of mi. Firstly, moment of inertia of uniform ring. Look at the figure. Here is the ring, and the mass or the object is rotating around this axis, and it is rotating in a circular manner or in a circular motion with circumference of this ring. And from this figure we can conclude that if this object is moving in a circumference of this ring, then we can say that the distance of the object to the axis of rotation, which is capital R, will not be changed at any point. Therefore, we can say that the formula of this is I is equal to mass into square of distance from axis, which is I is equal to mr square, and this is the formula for moment of inertia of uniform ring.